Welcome to the AM6X Security Overview video series. This section is Introduction to Secure Boot. Let's take a look at the things we're going to discuss in this video. First off, why Secure Boot? What does it do for you? What value does it have to the system? Next is setting it up. How do you have to implement Secure Boot? Then using it. How does the system actually go through a Secure Boot process? And finally, a summary. And this will give some tips and some ideas for things that you can use to further your knowledge. Security starts with trust. When you look at an embedded system, the first thing you have to understand is what are the assets? What are the valuable things in the system that need to be protected? Is it your intellectual property? Is it user data? Whatever it may be, you've got to understand what needs to be protected and then understand how it could be attacked. And this will help you come up with a layered approach or a defense-in-depth strategy for how to protect those assets from those threats. You're going to generate MIDI requirements, and that might possibly impact the hardware and the software design. And as you go through all of this, you're going to quickly realize, if I want to have a secure system, I need to know what software is running on this device. And that's going to require you to look at, how do I establish a hardware root of trust? How do I have something in the device or in the system that's going to make sure that the software that gets running on this device is the software that I want it to run? And that's a secure boot process. That secure boot process will authenticate and validate the software before it executes it to make sure that it's the software that you've said I want to run on this device. It hasn't been modified. It hasn't been changed by someone else. I know what it's designed to do and how it's supposed to do it. And that's going to help give me confidence that I can defend the assets in that particular embedded system. The AM6X processor architecture with several device families from Texas Instruments has an architecture that is based on security and safety. The elements needed to establish that hardware root of trust and do secure boot are baked into the architecture. They're one of the major components or pillars of the architecture itself, which is really necessary in order to have a secure system. The very first thing this device needs to do, it needs to be secure. If you ever have a time period when the device is executing that's not secure, that introduces an opportunity for hackers to get in and either inject code or do things that you may not want them to do, and that may give them access to the assets that you're going to store in that system. So architecture of the system really needs to have security baked into it, which the AM6X architecture does. Let's zoom in a little bit on what that security architecture looks like. And it's really a separate security controller that's built into the device. This security controller stores all of the secrets, and it does all of the operations, and it does so in a way where it's protected from the rest of the system. So if you're running a Linux-based device, for example, you don't want a rogue Linux process being able to get access to your secrets. So you put those in a security controller, and the architecture of the device using firewalls and other capabilities will make sure that the Linux application does not have access to this information. As you can see, the security controller is composed of processor cores, usually up to a dual-core Cortex-M type microcontroller core. It has a secure ROM, a secure RAM, some peripherals, and most importantly, probably for today's discussions, is a secure area of storage. And this area of storage is called one-time programmable memory. And this is immutable memory that can be used to help establish this hardware root of trust. We use the secure ROM in conjunction with the OTP, and that gives this hardware element to make sure that when this device turns on and starts executing, that it's only going to execute code that I've authorized for it to execute once it's been secured. As you can see, there's other elements of the security controller, but we've highlighted the sections that are really important for secure boot, and you'll see how these are going to operate as we go through the secure boot process. So hopefully you have a better understanding of why secure boot and why it's there if you didn't already. Now let's look at how is it going to get set up and how is it going to work in order to make sure that my system is secure. In order to do that, we probably should understand what non-secure boot is and why does it exist. Well, most devices, when they come from TI, they're non-secure. You haven't programmed any keys to them, you haven't done anything else. they're development devices. And that's the real value of a non-secure device is when you're trying to get your system working, get your code operating, you really don't want security getting in the way or making that more complicated. It's hard to do enough as it is. So non-secure boot really is a development device. It doesn't check the code as it boots. It's just going to run the code. It's typically done in a development environment where your intellectual property is being protected by other ways. There's no real user data usually stored on these devices. So the assets that you need to protect are being protected by other security mechanisms, if you will. So a non-secure device is a development device that makes it easy to develop your code and get that up and running. And then as you get ready and you start creating scenarios where you need to secure things, then you can move to a secure device. And we'll talk about how to do that in the following steps of the video. So in contrast to non-secure is secure, right? So we go from a system that will run anything if it can that's stored in memory at the address that you tell it to go boot from, to a system that only is going to execute something that's called signed code or authorized code. All right, so we're going to use cryptography to protect this operation so that we know when we try to go execute this that it has to have been signed off cryptographically to execute on this device. Otherwise, it won't execute. The boot process will stop and the device won't run anything, therefore keeping your assets secure. This allows you to use secure boot to establish that root of trust that we've been talking about, and therefore pass that root of trust as a chain of trust onto the following stages of boot. So you get your first bootloader up and running. If you have other bootloaders or other stages of bootloader, you use a similar technology to make sure that they are also valid and signed off on all the way through up to your OS and your applications. So that everything running on that device, even after an over-the-air update, for example, has been validated or signed so that you know it's code that you've authorized to run on this device. And therefore, you should know how that code operates, what it's supposed to do, and everything about that code you need to make sure that your system is running securely. So that's secure boot. Secure boot, like I said, uses cryptography and encryption to do this process. So let's take a quick segue into some of these basic operations just so you understand the concepts and can apply those to the secure boot process. As far as encryption goes, I think most people, when they think about encryption, in the digital world at least, they think about encrypting a file on your hard drive, right? And that's called symmetric encryptions. That's where you have one key, and you use that one key to encrypt and that same key to decrypt, kind of like the key to your car. The key needs to be kept secure, right? If you give your key to somebody and they know where your car is, they can take your car. Same kind of thing here. If they know where the key is, they can decrypt anything that you've encrypted and they can see what it is. So that's symmetric encryption. Another type of encryption is called asymmetric. And asymmetric is quite a bit different than symmetric, and it's going to be based on a pair of keys, a secret private key, the red key in the diagram, and a public key, the blue key in the diagram. And you're going to use both of those keys to encrypt and decrypt information. And this is also going to help you to know that if you encrypted something with the private key and you have the public key, that only the person that had the private key could have encrypted that content. So obviously, if they've done a good job of protecting their private key, then you know that that information comes from them and then only. And that's one of the major applications of asymmetric encryption is in signing messages. All right, and as we'll see, a lot of the secure boot information that we're going to use are like messages from the software to the system to make sure that everybody agrees that this is the appropriate software to run. So asymmetric encryption is going to be very important for the secure boot process. But please understand and note, everything's based in either one of these systems on either protecting the private secret key or in symmetric encryption, protecting the secret key that's used for symmetric encryption. If those keys aren't managed properly, this whole system falls apart. Some other concepts that come into play are hash, signature, and certificate. So let's define each one of those. The hash function is just a way to map an arbitrary size to fixed size values. And an example of this is SHA-256, which is very popular. It's like a checksum, but it's more secure. And it's also one way. So when you do a hash of an operation, you can't use the hash to learn anything about the information that you hashed. And And what this is nice is that you can take this arbitrary length and you can take it down to a fixed length, and you know something very specific about the content of that message. If you encrypt a hash with a private key in asymmetric encryption, this creates what's called a signature. All right, so this is digitally signing something. So you hash the content, you take the hash, you pass it through a asymmetric encryption algorithm with the private key, and now you could use the public key to learn information about that hash. And you would know that the person that used that private key is the only one that could have signed that content. Here's the example of using the public key. So in this example, we've combined a signature with the original content, and that's a certificate. All right, so this is some metadata on top of your normal image content, and we're going to use that metadata to decide, is this the content this person wanted me to have, or in our secure boot scenario, is this the content that I'm really supposed to be allowed to execute, or the code that I'm going to run. So we take a hash of the content, we use the public key to decrypt the signature. If those two hashes match up, then we have confidence that that content was the content that was signed by the person that sent it to me, or the developer that wanted me to boot the system, and also that it's not been changed because we use a hash. If we change the content, then the hash would have changed. And that would, of course, have changed this whole operation, and that would have made it where we couldn't boot securely in our example. All right, so we've covered the basics. So let's move on and look at how do you actually implement secure boot on an AM6X based system. And it's just a series of quick steps. And the first one is one you're very familiar with. You have to write your software and get it up and running. And as we discussed before, that's best to do on a non-secure device. Software development in embedded systems is hard enough without having to worry about doing it on top of security. So you can leave that security off as long as you're comfortable with not having to secure the system, and you can develop other aspects of your system. Once you have that software written, now you're ready to start securing it. So the next step will be to generate that asymmetric key pair. We're going to use asymmetric encryption to protect this operation, so we need a key pair. And we're going to do that typically inside a hardware security module. This is a hardware device that has been very secure. It's usually certified. It's been audited. It's been known to really protect secret content in the digital world. This is your safe, right? You're going to keep your private key in the safe, and you're even going to have rules about who can access that and when they can access it to make sure that that secret stays protected. So this is a hardware module, typically in your IT infrastructure, that you're going to use to sign software or do other security operations. All right. So a lot of times SOCs do implement a hardware security module function as well. This is not that HSM. This is a separate hardware security module. Think of it as a very secure computer that is going to store your secrets, and they're only going to be stored there. Now, for development, you could use your development PC. You could use an application like OpenSSL on Linux to create these key pairs, and you can store those certificates and keys, in the open on your Linux development machine. But obviously, that's not secure. If anybody were to be able to get access to that private key, your entire secure boot operation has been compromised. So you don't want to do that. You want to use industry standard practices, and that's going to always include using a good hardware security module to protect your secret information. So if your HSM is involved and it's got your private key, obviously we're going to have to send some information to the hardware security module so that it knows how to create the certificate for the secure boot process. So we take our bootloader image, and we're going to sign that bootloader image. So we're going to pass either it or a certificate that was built non-securely off to the HSM, where the private key, the real private key, can be used to generate a true private certificate. All right, so we take information about our image, namely that the hash is the most important. So that's going to keep track of whether this is the image that I want to be able to allow to boot on my systems. Take the hash of that, pass that through the private key, and write that as a digital signature on an X509 certificate, which is an industry standard. All right, so you can see some of the other information that is put in the certificate, namely the public key that you're using, because we're only going to store a hash of the public key in the device. We'll see that here in just a second. But the most important thing that you see there is the image hash. All right, so that's what we're going to use to make sure that this image has not been modified or altered in any way, and it's the image that we want to make sure that we're booting. We need to now write not only the image, but also the metadata or the certificate into the flash, because the ROM bootloader in the device is going to use this information to boot. If you have security enabled and you don't have that certificate there with the necessary information, the device is not going to boot. That's where secure boot comes from. So now we take all the metadata, the image, we put that into the flash on the device, and our last step is we need to actually program the public key, or the hash thereof specifically, into the device and turn on security. So we take our public key from our HSM, we write that into the device, and then we turn on security. Once we do that, this is a non-reversible operation where this device will only now boot code that has been signed by the private key that goes with the public key that it's been programmed with. And that's the process to implement a secure boot operation on an AM6X class device. All right, so we've got it set up. You've seen all the steps necessary to do it. Now let's look at how that actually changes the boot process. All right, so here's our system again. We know that we've got our signed bootloader programmed into our flash. We've got our device with the public key hash programmed, and we've got the device secured. All right, so now when we turn the device on and we want to boot, the first thing we're going to do is validate the public key. So the public key that's in the certificate programmed in Flash, we're going to hash that. And we want to make sure that that matches the public key that's programmed inside the device. If those don't match, we're going to stop. We're not even using the same keys. There's no reason to continue. Next, we need to validate the certificate itself, right? We want to make sure that somebody didn't come in and insert a new image hash into it, for example. So we want to validate the certificate itself using the signature. The signature was signed with the private key. We'll use the public key to decode that, and we'll be able to see whether the certificate hash and the hash that comes out of decoding the signature is going to match. If they match, that means the certificate is the one that was signed. And then lastly, of course, we can use the image hash that we know has not been altered because the certificate was valid. And that means that our bootloader image that's been stored in the device, once we hash it, we can compare the hash that was put in the certificate. We know that this is the code that was signed. And we know that this is code that's been authorized to boot on this device, and we can go ahead and continue a boot process. All right, so that's how the device actually goes through a secure boot operation. We've got that covered. And now we can wrap this up. So we talked quite a bit in this short video. We talked about how secure boot is really required for you to know what software is running on your device so that you can trust it, so you know it's authentic and valid. We leverage the root of trust concept of the secure ROM that's in the device and the OTP programmed public key hash that's in the device to make sure that that device will only execute further code that has been signed appropriately for that device. Because secure boot is so fundamental to embedded system security, it's included in standards and regulations all over the place. In fact, I can't think of one that doesn't include secure boot because it literally establishes trust of that software, and software is such an important part of an embedded system. It's probably obvious, but it has to be said that private key management is paramount for this process to work. If you're sloppy with your private keys, you have no security. If an ex-employee or a disgruntled employee or somebody could hack into your systems and find these keys, they could use this to create whatever images they want, to be able to put code on your devices, possibly do a secure update, whatever they might be able to do if they get access to that private key. So using a good HSM, using appropriate procedures and policies to make sure that that private key information is kept secret is very important, and it's the linchpin of this whole process. All of this is available today on the AM6X architecture and the devices that are within that family. And the process is very similar across that family. Some of the architectures are a little different, but the overall process as we've discussed it today is exactly the same. So you can learn about the process in one device and then quickly carry that over to other devices within the same architecture. And that allows you to confidently gain your expertise in security. And if you want to get started to do that further today, we have a Security Getting Started Academy, where you can go and actually do this. If you've never done it before, you can use some keys that TI provides that are just out there in the public as examples that you can try. So you can sign software, you can program those keys into a device, and then you can verify the secure boot operation and see how that changes the boot operation itself. And then you can also, given that device is now secured, you can use JTAG you can use a certificate to unlock JTAG, so you can still debug that device and see how that by creating that certificate, you're only able to get into that device using JTAG with some secure information based on the keys that have been programmed in it. And you can see that there's a list of the links. We'll provide those on the webpage for the presentation as well, so that you can go check out those for your favorite family. And as I mentioned earlier, these step-by-step instructions are almost exactly the same for each family member. We provide them as options for each one so that you can quickly go through on any given board of your choice to go through this. But the overall process is the same. Once you learn how to do it on an AM6-2X, for example, you're going to find that doing it on AM6-4X or one of the other family members is very, very similar. And that'll allow you to reuse your security learning so that you can apply security to all your systems, because that's becoming very popular and very important in our world today. And that's going to wrap up our presentation. I thank you so much for giving us your time today. I know it's extremely valuable. I hope you found this useful. And I hope you'll go off and try one of those Academy modules and implement your first secure boot if you've never done so before. And if you have, I hope you'll see how easy it is to do on a TI device. Thanks again for your time. Have a great rest of your day.